All right, let's look at, I'm not sure what number this was. Number 13. The first thing I want to do, obviously I'm going to, or we're going to come up with what the equation looks like here, but then I want to graph it and see if we can then mimic the results that our graph shows us. I think that's very important to be able to do. So the first thing, and I honestly believe that this question, the order of A, B, C, D, and E could be a little bit better on their part. Okay, I think it makes sense to solve for E, like right here. Okay, and then do C and D, and that's kind of how I'm going to approach this. But it says ball is thrown straight upward at an initial speed of 80 feet per second. Use this formula here that we've talked about to do so. It says if, gives you something about if not possible, enter impossible. Okay. So first thing we're going to do is say H. I'm going to write, because this is a function. Now, they don't write it this way, but I'm going to write H of t, because we haven't talked about functions yet in this course, but you have had Algebra 2, which is basically an entire year of studying functions, meaning that it passes the vertical line test, meaning every x value has one and only one y value. My computer just unmuted itself. It's weird. Okay. And the reason I want to write it this way is because we're going to input a t value, and that should give me a height here. Okay? The t value, the height is dependent on the time. Okay? So it says initial velocity is 80 feet per second. So we're going negative 16 t squared plus then 80 t. And the first question says, when does the ball initially reach a height of 96? So that's what we're looking at. When does it equal 96? Okay. I'm going to, so there's kind of two approaches to this graphically. Okay. We can look at just this side here as a graph, and that side there as a graph, and see where they cross. Okay? See the t, it would be the x value of my graph, but that's going to be the time in which they cross. Or we can rewrite the formula or equation as this, and then see this as a graph, and that as a graph, and again, see where they cross. Does that make sense? This is actually what you would be doing if you did everything by hand, okay? If you took the analytical approach and just knocked that thing out with the quadratic formula or factoring, it looks like it's going to factor pretty nicely. 80 and 96 are both factors of 16. But if you're going to use just the graphical approach, I think maybe this makes more sense because this is really what's going on. If I type in negative 16 x squared, and I don't have it, I can't use t on here. It's got to be, everything's got to be x, plus then 80x. And I just want to focus on the first quadrant here. Zoom out. We'll mess around with the axes a little bit here. So we get that thing right there. And because, remember, this axis here is no longer the x-axis. This is our time axis, okay? and this is our height at specific times. Does that make sense? Okay. So every one of these points on here, say that point right there, maybe that's a time of 4 and a height of, I don't know, maybe about 70. Okay. If I wanted to see where this was equal to 96, the idea is to graph a second line, y equals 96, and I get that right there. Okay. Now I'm going to ask for the 2 points of intersection here, for that line and that curve, and you see that it gives me A and B to be 2 and 3, x values of 2 and 3. So at time 2 seconds, this thing reaches 96 feet. Then after 2 seconds, it starts to reach its apex, its maximum height, and then it starts to descend again, and it'll go back through a height of 96 at 3 seconds. Does that make sense, everybody? Okay. So that's the physical concept of what's going on here. Okay. That curve is showing that ball's movement up, okay, and down across time, okay, against time as your independent variable, okay. So now the next thing I want to do is actually go through and see if we can replicate those answers with this information here, okay. So what we end up doing is we take this here, and I'm going to divide everything by negative 16, okay. So it's going to be 0, t squared minus 5t, okay, plus 6, right? Now, if I factor that, I'm going to get t minus 2 and t minus 3. So that's where you see time 2 and time 3. Now they say, when does the ball initially reach a height of 96? So because those are times, the initial time is 2, right? We're talking about initial, or usually it's an idea of like 0, time 0. But when we have answers like this, the initial one is the first one. First one you come across, so time 2. Does that make sense? Okay. Now, if I were to, just to draw a comparison, if I were to graph that one there, that's a different graph than that one. Okay? Because because that minus 96, we're basically dropping it 96 units. But let's see what that would look like. If I had negative 16x squared plus 80x minus 96, it'd be that red curve, okay, which is no longer kind of the physical thought of what is going on here. Does that make sense? Okay, we've adjusted the physical thought, which was the green, okay, with the ball going up and coming back down over a certain time. But now if I set that equal to 0, so I'm going to graph the line y equals 0, okay, and we can see then that we take the red one, set it equal to y equals 0. Do I still get the same 2 and 3? Does that make sense? Okay. So the solutions to this red one, whenever we take an equation and we manipulate it, we change both sides the same way, it's going to change the graph, okay? But the intersects, the solutions of this green one still exist inside the red one. And that's the idea of every time we work through and try to simplify an equation, in the background, in the graphical aspect, we're changing the graphs. But the solutions to the first initial one should always exist in our final one. Okay? So that's that part of that question. Okay? Now the second part says, when does it reach 192? Okay? Well, if I look at this graphically again, let's just look at the green one. and I look at the maximum height of this. Okay, so the maximum height is, you know, a little bit bigger than 100, right? 192 is all the way up here. Does it ever touch 192? Does it ever go through that line right there? No. Okay, so graphically speaking, that's impossible. Let's do the work, though, to guarantee that. Because on, like a final, if this was questions on final, what we're going to have is a rubric to grade your work. And if you just have the answer impossible, I maybe can give you 1 point. But if you have the work that supports impossible, I can give you like 10 points. Does that make sense? Okay. And your calculator is never going to be sufficient work. Okay. I think it's good to use the calculator to recognize ideas. And I like to do that because I absolutely know the answer before I do anything, right? And now because I have a parabola and I know there's no answer to this, when I do the work, I should get imaginary results back. I know that's the link between the equation and the fact that they're not going to the two graphs are not going to intersect. Does that make sense? So I'm going to go, they said 192 is equal to negative 16 t squared plus 80t. So that was the picture that we just had. I'm going to amend it. I'm going to adjust it by subtracting 192 from both sides. Okay. Then I'm just going to see if 192 is a factor of 16. It is. So again, that's nice. And I get that. Okay. And now the question is, well, what are two numbers that multiply together to give me 12 and have to give me negative 5? Well, they both got to be positive, or they both got to be negative, and there are none. Okay, so I'm going to resort to the quadratic formula. And then when I do that, okay, so I get 25 minus 36, right? Or sorry, 25 minus 48. So I get 5 plus or minus 25 minus 48, what is that, minus 23? All over 2. And this thing here is called the what? Discriminant. And if the discriminant is less than 0, you have no real solutions. Okay. Now remember, so when I highlighted that, and this is coming up in one of the early questions in the assignments, that when you ask you like capital D, the discriminant equals, a lot of you are typing in the square root of b squared minus 4ac. Okay. The discriminant is not the square root. The discriminant is just the radicand. It's just the b squared minus 4ac. Does that make sense? Okay. So that's why we know that that's impossible. That's the logical math that supports this picture. Okay. Does that help? All right. Now the next question says, what is the greatest height reached by the ball? Okay. We're going to have a couple different ways we can do this. And we could answer that first. We could answer this next and then this final. But I think maybe going off of symmetry is the easiest for some of us to get these solutions. So I'm going to do this one first. It says, when does the ball hit the ground? If the ball is hitting the ground, what is h of t when the ball hits the ground? It is 0. Okay? So this is the exact same as question A, question B, okay, except for where it says 196 or 192. Now it says 0 feet. Okay? So we're going to go, let's do E down here. So it's h of t, negative 16t squared, plus 80t, but now this is 0. I'm going to factor out a negative 16 out of both these. and it should give me that thing there, right? Now remember, this is still two factors. That's still a factor. And obviously, that is as well, okay? So we're going to have negative 16t is equal to 0, and t minus 5 is equal to 0. A lot of people, especially when that doesn't have a coefficient, like if it was just a t that we brought out, a lot of people forget that that's a factor, and that's producing a 0 of 0. Divide both sides by negative 16, t is equal to 0. This one here, t is equal to 5. So if we were to graph this, wrong one. If we were to graph this, we have at time 0 an x-intercept, and at time 5 an x-intercept. Okay? Now I'm not going to make my x scale and y scale the same or anything like that. I'm not even going to use my y scale right now. But we should know that, so our parabola is coming up through here through 0, and then to go back through 5, because it's concave down, right? This negative a tells me it's concave down. So it's going to reach its maximum somewhere, and then it's going to come back down through that, right? Okay? We talked briefly, been a couple days now, that point right there, that is your maximum. It is always on that line right there. That line is called the axis of symmetry, which is always halfway in between your x-intercepts. Does that make sense? Okay. So that time is going to be 2.5. So down here, when it says when does the ball hit the ground, I obviously found that as 0 and 5. And then the maximum exists at a time of 2.5. So there you can see answering part D with that logic, right? Okay. Now I want to know what is the actual height. Okay. Well, remember, this is why I've been writing this as h of t is equal to negative 16t squared plus 80t. Because when I plug in a t value, okay, end of this thing here, it's going to give me a height at that t value, right? So the notation we use is that h of 2.5 is equal to negative 16, 2.5 squared, plus 80 times 2.5. Okay, if we work that out, negative 16 times 2.5 squared, that gives me negative 100, plus then, so 80 times 2.5 is 200. So this h at 2.5, so the height at a time of 2.5 is 100. That kind of make sense? Okay, so this ordered pair right here, we said it was an the t, comma, h of t, and for us, t was 2.5, h of t is 100. So that's where we're getting that number there. Okay? All right, that's one way of doing it. Not the only way. If you remember from last year, okay, your vertex of any parabola has an x-coordinate at the opposite of b over 2a. So in this case now, it's not going to be x for us, it's going to be t for us. So I'm going to say t is the opposite of b over 2a. Let's go back to the equation we had. We had that, right? If I take the opposite of b, being negative 80, and divide it by 2a, which would be negative 32, right? Negative 80 divided by negative 32 is obviously a positive number. 80 divided by 32 generates a time of 2.5. Okay? So vertex for any parabola, I'm going to give this formula, for any parabola is at, so the x-coordinate, you call it the independent variable, is found at the opposite of b over 2a. And then what you do is you plug in the opposite of b over 2a into the function to find the height. Does that make sense? So if I were to take 2.5 now and plug that into negative 16t squared plus 80t, that's going to give me that y value that is symbolized by f of the opposite of b over 2a. So there's alternative, and I want to show these things. I want to show the alternative approaches, guys, because let's say I get on a test, my hope is that we use that formula because that's the quickest. Okay? I hope we use opposite b over 2a. Hopefully that ends up being eventually common knowledge. I'm not saying it should be now, because last year it might have been, heck, it might have been like October or November that you talked about it, and you haven't used it very much since. Okay? To the extent that we're going to use it, though, that should end up being common knowledge. And that we use that. But maybe you struggle, and you're not, my work doesn't make a whole lot of sense. I'm not convinced that this is the right answer. Could I then use the symmetric approach to see if I validate my work? Does that make sense? There should be multiple approaches to pretty much everything we do that can allow you to validate one approach against another. Does that kind of make sense? Okay. Now, obviously this question would not be, all these parts would not be on the ACT. But guys, if you had your TIA 384, this should be something that we can find the answer for pretty quickly. I want to show how to use your TIA 384. It's a pain in the butt at first because of how we have to like adjust our window and all that kind of stuff. Okay, so I'm just going to go y equals. Let's just deal with that first part where it said when does it like equal, I think it was 90, was it 96 feet or something like that? If I should type in negative 16 x squared plus 80x into that, and then I'm going to put 96 into y2. Now, if I am going to use this calculator, because of the nature of having to adjust the window and zoom out, zoom in, zoom out, zoom in, that kind of thing, to really see what's going on, it would actually make more sense, guys, to just put the 96 and go negative 16x squared plus 80x minus 96 in y1, and then put 0 into y2 and just see where those two things cross. Okay? But to see kind of the first way we did it with GeoGebra, kind of maybe draw a comparison of how much more difficult the calculator is to manipulate. But if I'm going to hit graph, and here's the thing, most of your graphs are probably set up to a standard view, where that is not very good, right? Okay? Now, we know we were looking at 96 there, right? Y equals 96. So I'm going to go to Window. Okay? My X minimum, if I look at that again, and this is something that kind of keep track of, does the graph, is it important over here? I'm not seeing anything over there, right? So my window on the x-axis probably shouldn't be negative 10. Okay? My x maximum, again, looking at my graph, I'm halfway in between here. So maybe I don't need all of these, right? So maybe I'm just going to go my x maximum, let's say 6. And these are just, hey, you might have 7, you might put 5. Person to person might be a little bit different. Okay, now X scale, what that means, my X scale is set at 1. That means every hash mark I see here on the X-axis is 1 unit. So that's 1, that's 2, 3, 4, 5, right? Make sense? Now, the Y-axis is the one that's more difficult. My Y minimum, again, I don't need anything in the bottom quadrant, so I'm going to adjust that. And sometimes I got to mess around with it a little bit. But if I just put like 0, here's the issue with this. There's going to be some, eventually, there's going to be some words down here at the bottom when we ask the calculator to do some functions. And if I put this at 0, that means the line is going to be down here, and my words and lines are going to be overlapping. And one of them is going to be hard to read. Now, my scale is still by 1. So that's 1, 2, 3, 4, the negative direction, and this goes to 10. I want it to go to an X maximum of at least 92. Let's go up to like 120. Now, if I leave my Y scale alone, I leave my Y scale at 1, show you what the graph does here. It makes my Y-axis very thick, right? And basically what it's trying to do is put a tick mark for every integer between 0 and 120. Well, I don't even have 120 pixels on my calculator, so what it does is just shades it in as a double solid line, basically telling you that you should probably change your scale a little bit. So let's change our scale. I'm going to say 20 here. And what that's going to do is now every time I see a tick mark, that's 20, that's 40, 60, 80, and there's 100. Does that make sense? Okay. That process, if you're not comfortable with it, there's kind of a learning curve with it. It might take you a couple times to mess around with that. You might change your window and think, okay, that's what I want, and then graph it, and your vertex or something still doesn't show up. And then you got to go back to your window, readjust, go to graph, see if it shows up, and kind of maybe bounce back and forth between that process over and over again. Now what I want to do is find those points of intersection. So if I go second, and then up here to that button right there, which is going to take me to the calc options. Okay, this is, if you're going to use this calculator, this is a pretty useful series of functions. We're going to try to see where these two lines intersect. I'm going to go down to option 5. And now you see that it says first curve, and as I move along with my directional pad, you can see that cursor moves along the parabola, right? If I hit the up or down keys on my directional pad, it's going to jump me to the other curve. Okay? It doesn't matter which one that I select as my first curve. But what I'm going to do is I'm going to select a point on this first curve that is close to where I think they intersect. And I'm going to hit enter. And then I'm going to do the same thing on this second curve. I'm going to hit enter. I kind of explain what this is doing for us. So our calculator right now, we have just defined for it a region to kind of analyze. Okay, we're asking it, look at all the infinite ordered pairs kind of in that region, and look for the ones that have the same y value. And the ones that have the same y value spit back to us the x value that goes with that. So if I hit enter, okay, the y value that they both had was 96, and the x value that went with it was 2. So there's your solution of 2. Does that make sense? You can then do the same process again to find that one there of 3. And that's how you would address that if you were on the ACT or something like that. The ACT, in my opinion, is kind of stuck in the dark ages with the technology. The TI-83 has not changed since I mean, like we got the silver edition, we got the plus, we got the 83, the 84, we got the color edition, but they're all the same. Okay, there's really no change in those things since before when I was in school. Okay, so you know, early 90s when TI came out with this calculator, they haven't changed it since then. Okay, almost 30 years. GeoGebra, Desmos especially. Desmos is, I think, if you research anything about Desmos, they're kind of putting TI kind of up in a corner because Desmos is free and it does a lot more than TI does. And really the only thing that's got Texas Instruments still surviving with this platform is that it's mandated on the ACT. And everybody's got to take the ACT, right? So that's some economy market stuff for you. But there's an option. I don't care, you guys, on tests and quizzes. You want to use Desmos? You want to use GeoGebra? Go ahead and do that. Okay? But at the same time, I do think we should work a little bit with that TI 83, 84 for when you do get to those that ACT test. Does that question make a little bit more sense now? Okay. Again, just seeing one of those might not be enough. Okay. But again, you go home and you're working on this one. Okay. Pull up the video if you're struggling. See it again. See that discussion again. Read through your notes. Did we do this one yesterday? The 2 pi r squared h one? We did? Okay. When we typed that in yesterday, I just want to, because when we type it in, it looks nothing like this. I think we ended up with, and I could be wrong, like 2 pi, see if you remember what we had there. I don't know if I still have it written down somewhere. Let's just do it. You guys mind doing it real quick? Okay. You know what, I've got, this is the reason I'm doing this. I'm using OneNote, so it should be saved here somewhere. There we go. We got this thing here. And it looks nothing like what they typed in, right? What they do, and we kind of glazed over this because it doesn't matter how you type it in. You type that in, it gives it to you correctly. What they end up doing to get their version, and I'm not really sure the logic here, other than it makes your denominator smaller. They see that this, those two things have a common factor in them, right? So they rewrite this as, they pull 4 pi out, and then they have pi h squared.
Alert system in preparation for today's practice lockdown drill at 9 o'clock. This is only a test.
We have practice lockdown at 9 today. So it's really good when something's going to happen that we can hear that, right? Like that's okay. So pi h squared is what we get when we factor this 4 pi out, and then here when we factor 4 pi out, we're going to get 2a, right? All over 4 pi. Then what they do to get their answer is, I have 2 pi h plus or minus. Now this is a product of two things under the radical, right? So you can write that as this. Over 4 pi. And now that one there, does that have a perfect square in it? So you take the 2 out, so you get 2 pi h plus or minus 2. Now the pi still stays underneath. That's not a pi. Pi stays underneath. Then we got pi h squared plus 2a all over 4 pi. And now can I cancel that 2, and the 2 there? So that's where they get their solution. Again, Is it good to maybe do that algebra and have the capacity to do that algebra? I think so. But that's kind of a simplification process that's really unnecessary right now for this question. Other questions on here? Anything that we haven't covered that... Did we talk about this one? Did anybody struggle with that one? Yeah, multiply that one by the LCD, right? You want to do that one? Let's see here. All right, so if we're going to solve that thing for R, we need to get rid of the fractions. So what we do, if you remember from last year and year before, you go through your denominators and you pick off the factors that are new, okay? So when I look at this first one, obviously that R is a new factor, right? So that's going to be part of my LCD. Now, as I continue to go through, there's another R, right? There's an R squared. You guys remember which one you take, R to the first or R squared? R squared. So if I just take R, and then I get to that last factor of R squared, that last term with the R squared in it, the R's will cancel out, but I'll still leave with an R in the denominator of 12 over R. Does that make sense? And that's still a fraction. So that's why I need the largest power of common factors. So I need the R squared, and that's going to take care of that one and that one. And then I need, this is 1 minus R as I move through there. That's a new factor as well. Okay? So those are the factors that I'm going to use. That's the LCD. And I'm just going to, I just feel more comfortable rewriting that. I know it's more effort, more work, but rewriting it for every single term so that I can visualize what is getting canceled out in each one of them. So that R will cancel with just one of those, right? Leave me R times 1 minus R times that one. Then in the second one, that 1 minus R is going to cancel with that 1 minus R, and it leaves me just an R squared times the 6. And then over here, the R squared is going to cancel, and leaves me 12 times the 1 minus R. Now all I have to do is distribute. And because I see the R squareds there and there, I'm going to factor. So I need to get everything equal to 0. So we'll have 5R squareds. When I merge those two together, I'm going to move that 12R to the other side, so it'd be positive 13R. And I'll move my 12 over as well. So minus 12 is equal to 0. I look for GCF. Not everything is divisible by 5 here, so that's a problem. Maybe I do the AC method, so I get negative 60. Think of numbers that multiply together, give me negative 60 and half is 13. There are none.
Teachers and students, at this time, we will be proceeding with our practice lockdown drill for today.
So R is going to be negative 13 plus or minus 169 minus 4 times A times negative, negative 12 over 10. We're safe. So then obviously you just have to simplify that. 169 plus what's going to be 60, 240. Somebody just check in. Who was it?
All right, teachers and students, at this time we are engaged in our practice lockdown drill. Again, at this point, teachers, we should be securing all classrooms with our night lock devices. Students, as a reminder to you during today's drill, if the teacher is not present in the room at the time of the lockdown, you are to go ahead and secure the room. So this is one of the circumstances, along with the substitute teacher. If they don't know the procedures, in which students are permitted to grab the night lock devices and secure the rooms. Again, looking at a review of our Alice, at this point we would be alerting you of what is going on with our lockdown. Again, the alert part. Teachers and students, at this time, based on our information that we would be giving you, if it would be safe to evacuate the building, we would also have that option. So, for example, if something was going on in the science wing of the building, the teachers and students in the front end of the building, if it was secure to evacuate, at that point we could do that. Teachers, we would leave the